Hi there, Science 10 and Chemistry 11 students. Again, there's this very short overlap between what you're covering, so this lab and lesson will apply to you both. Today we're going to look at types of chemical reactions. There's a slightly higher level of detail I'm going to call on you Chem 11 students to be familiar with, but it's going to be pretty similar in terms of my expectations for you and the lab write-up that I'm going to put onto teams. So there are a number of different kinds of chemical reactions. In fact, there's many kinds, though in your typical high school science class, we're looking at inorganic chemistry, not the chemistry of carbon-rich molecules. At least we don't look at that very much. Organic chemistry has piles of different kinds of reactions that we're not going to examine. We're going to focus here mostly on organic chemistry with, mostly with metals, acids, and bases, and so forth. So the kinds of reactions I'd like you to know are written here on the board. I'd like you to know synthesis, decomposition, single and double replacement, neutralization, and combustion reactions. So those are your 6 types of reactions that I'll be looking for you all to be familiar with. I described them in your notes. There are some listed in your notes, and I'm looking for you to be able to balance them. You've all just done balancing chemical equations, and so be working from that. I'd like to go through some examples, though. I use a kind of like some symbols for it, and then I want to kind of give them a bit more realism. Notice that there might actually be a few corrections to be made to my notes, but what I have up here is your master copy. So first kind of reaction I'd like you to be familiar with is this right here, the synthesis reaction. It's that AB thing where I might have a couple typos. For a synthesis reaction, you're putting things together. Synthesis, that really means that, a joining of 2 things to make something else. Here we imagine 2 elements. Element A and element B are joining in a chemical reaction, which can be exothermic or endothermic, and creating some new chemical compound. The example given there is the combustion of carbon to make carbon dioxide. In fact, I decided I was going to set this one up. It's a nice simple reaction, and it's the first reaction you're going to look at today. So getting my striker here set up, get the Bunsen burner going. What we have right here is elemental carbon. It's from my wood stove. I washed it to get any ashes off, so we shouldn't get any smoke. When you're burning charcoal in your wood stove, you're actually not creating a whole lot of smoke. You're not creating a lot of particulates, at least if your damper is set properly. So here we'll see this combusting, but what you should be looking for when you're burning charcoal is for it to seem as if it is simply disappearing. In reality, what's happening is the carbon is combining with oxygen that happens to already be in the air and creating carbon dioxide, which then disappears and becomes part of the atmosphere. So let's have a look to see what that looks like. And there. Do you want to try holding the computer?
Yeah.
Okay. I want you to hold the computer so that little dish is in the middle. Okay? You got the entire weight of the computer?
Mm-hmm.
The whole weight of the computer? Okay, because I don't think you have here. I'm helping you a bit. So,
Whoa.
students, I'd like you to take note that you see this combustion reaction right here. This is a combustion reaction, and it's also a synthesis reaction. Let's try and get a good look here. I need you to hold the entire weight of the computer because you're not right now. Okay. So let's bring this back a little bit. You've probably all seen this before, but maybe not thought upon it a whole lot. You're seeing what we see here is these red hot coals. that just means that we're bringing the coals to a very high temperature. But the other thing that's more relevant to you taking chemistry is that we're seeing chemical change here. You're actually seeing that charcoal disappearing. That disappearance is how you're witnessing the chemical reaction. The charcoal is disappearing, and in its place, we're creating carbon dioxide, which is entering the atmosphere. This is a synthesis reaction, taking the two elements together and forming the one new compound, carbon dioxide. The opposite of a synthesis reaction is a decomposition reaction. I don't have one of those. I don't have one of those set up for you here. I will be showing you one later that it will be part of your lab activity. But I'll describe it anyways. Just have to turn the lights back on. Now, I'm not an expert in the field, but I understand that something gets used a lot in industry to make cement, to make concrete that we need for walking on streets, is a lot of limestone. And, I stand to be corrected, but I think the way that it's done is they actually have to heat the limestone up a lot and to create calcium oxide. You can all look that up later yourselves. The point is that is an example of a decomposition reaction, because limestone chemically has a chemical formula of calcium carbonate. This is the same stuff that chalk is made out of. Now, what you can do with that calcium carbonate is you can pulverize it and you can make it into a powder. You can then expose it to a great deal of heat and it will break up into its constituent parts. Please note, by the way, this is already a balanced chemical equation. Calcium carbonate is CaCO3. When it decomposes, you're forming calcium oxide, CaO, and CO2. Gas, by the way. So that is a compound, AB, breaking up into A and B, two separate compounds. Hey, by the way, notice what I also did here. This is more relevant for you in Chemistry 11, but listen up, Science 9. I also put in the physical states of these substances. The little s means solid. Basically, CS means solid. O2G means gas. And CO2G means gas. In other words, solid carbon reacts with oxygen gas to create carbon dioxide gas. Some of the chemical equations, the balanced equations you'll see here, I've added physical states, some I have not. Chemistry 11, I will look to you to be able to add physical states, including AQ for aqueous, or dissolved, in your balanced chemical equations. So, synthesis and decomposition, the opposite of each other. The next kind of reaction I need you to be familiar with is the single replacement reaction. In this reaction, you have a pure element that is reacting with a compound. That pure element becomes part of the original compound, but then an element that was part of the original compound then becomes a pure element. Most commonly, you'll see this, at least in a high school science lab situation, as a reactive metal reacts with an ionic compound that contains a metal itself. The ionic compound, the metal that's part of it, gets freed up and becomes a pure metal, and what was a more reactive metal then joins up and becomes part of the ionic compound. There's a lot of variance on that, however. For example, if you add reactive metal to an acid, this is another example of where we'll see a single replacement reaction, but in that case, what's happening is hydrogen gas gets liberated. There's also another kind that you don't see discussed very much, but it's still single replacement reaction, where again, you have a reactive nonmetal that is reacting with an ionic compound. But instead of replacing the positive ion, like a metal would replace a positive ion, that nonmetal that makes a negative ion replaces the negative ion in the ionic compound. I'm going to show you an example of that right here. So here's two examples, in fact, of single replacement reactions. They can have two possible skeleton equations. One is A plus BC makes B plus AC. Imagine A is a metal, and B is a metal, and C is a nonmetal. BC is an ionic compound. So, an example, magnesium plus copper 2 chloride reacts to make magnesium chloride plus elemental copper, pure copper. That's a single replacement reaction of the kind that you will most often see and you already have seen. However, if A is a reactive nonmetal, the skeleton works out differently. It can be described as A plus BC, BC is a compound, makes C plus BA. Okay, I need an example, Mr. Coop. Here's an example. Chlorine, which you know to be a reactive element, reacts with sodium iodide. Notice this is going to be a balanced chemical equation to create sodium chloride, table salt, and iodine. In fact, what I've got here as a demonstration of a single replacement reaction that's not part of the lab is I've got that set up right here. Water, sodium iodide, sodium iodide is very soluble. And we don't need very much of it for this reaction. All I want you to see about the sodium iodide is that it creates a clear solution. In general, you're going to expect your salts, your ionic compounds of alkali metals to be very soluble, and sodium iodide is. If we were to let this sit here, it's starting to become a bit more clear. Now, we also have this here in the chemistry lab, which I think is pretty cool stuff. It's chlorine water. Which is a little counterintuitive. How could you take chlorine and put it in water? Well, it turns out actually it is fairly soluble in water. You'd expect it to react with the water, but it actually it stays as a pure element when it's dissolved in water. You can react it with hydrogen to make hydrochloric acid, however. Now, that's a separate story. So I'm going to take some chlorine water. First of all, I'll show you the color. You can even see through the tube right here, through the pipette, that it's another clear liquid. The only way I know that this is not just good old water, other than the labeling, is that it's got a smell. It has a powerful smell of a swimming pool. We add it there to the sodium iodide solution, and we've got a really obvious color change right there. This, in fact, is the color change we would associate with iodine. Elemental iodine, when it's in a dissolved form, is this kind of an amber brown color like you see right here. They're showing up pretty well right there. You can see that amber brown color. That was a single replacement reaction. Chlorine plus sodium iodide makes sodium chloride and iodine. So, single replacement reaction. You see there's three different kinds. A reactive metal in an acid makes hydrogen and an ionic compound. Reactive metal and ionic compound makes a new ionic compound and a new pure metal. And this one, reactive nonmetal and ionic compound, makes, again, a new ionic compound and a less reactive nonmetal. In this case, iodine was our less reactive nonmetal. Chlorine is a whole lot more reactive than iodine is. All right, so that's your next one you need to know, be familiar with. Next one I'm just going to describe to you and not show is this one, a double replacement. I'll show it to you later, but not right now. Double replacement reactions, I always liken it to this. I describe a situation where there's a ball and you've got partners dancing with each other. It's all very nice. And the dancing stops, or music stops, I guess, and the dancing stops. And then the dancers switch partners. Double replacement reactions are like that. Here's this here, AB. is like an ionic compound. A is your positive ion, your metal. B is a nonmetal ion. C is another metal. D is a nonmetal ion. They then switch. A bonds with the D nonmetal ion, and C bonds with the B nonmetal ion. What does that look like? I urge you to look at a picture of this. I'm not going to show you this reaction because it involves poisonous reactants, and I don't want to go there. The substance here, center screen, is lead 2 nitrate. Notice I put AQ for aqueous. It might react with sodium iodide, also in an aqueous form. These are 2 clear solutions. Again, what you get out of it is actually pretty cool. You get lead iodide and, sodium nitrate. I made a mistake. You get lead iodide and sodium nitrate. The sodium nitrate is extremely soluble stuff. Anything with a nitrate ion is really soluble. Anything with a salt from an alkali metal is really soluble. Sodium nitrate is absurdly soluble, but lead iodide is not. Often your salts of very heavy metals have quite low solubility. They form very stable crystals as ionic compounds, so they don't stay in solution. They can dissolve a little bit. A little bit of them will stay in solution. So if you were to, say, have a solution of lead iodide or lead chloride, and the lead iodide's at the bottom, you still wouldn't want to drink from it because a tiny amount of that lead is still in the solution. But most of it stays in the solid form because it has extremely low solubility. The only reason I bring up lead iodide is because, like many transition metal ions, it forms very colorful ionic compounds. Traditionally, lead iodide as a compound was used in paints because, and you should check this out, it gives a brilliantly yellow color. It's a classic chemistry demonstration. Take these 2 clear liquids and pour them together, and this very dense cloud, really, of yellow powder sinks to the bottom. In the past, painters used to use it. If you mix it with oils, you get a long-lasting and brilliant yellow color. But I think even some of, Van Gogh's, his getting a bit crazy, was partly blamed on lead paint. I don't know if that's accurate or not, but some people brought that up. Another kind of reaction I'd like you to be familiar with, in fact, you'll become very familiar with going forward into Chemistry 12, a bunch of you will be there, is a neutralization reaction. So what does that look like? It's a little bit like a double replacement reaction because, again, we're switching partners, but the dancers that are involved here are very different. The substances that are actually reacting are acids reacting with bases. Acids, as you know, you often think of an acid as a really reactive substance. Some of them are, but when you have a cold, a lot of people will be very happy to consume acids because you're taking vitamin C, which is ascorbic acid. Not all acids are incredibly reactive, but what they do share in common is that when they're in solution, they dissociate into a negative ion and, here's the important point, a hydrogen ion, a positive ion. Bases are, in a way, the opposite. When a base is in solution, it produces hydroxide ions. Think about that. Your hydrogen ions are H+. Your hydroxide ions, you might remember from your table of polyatomic ions, are OH-. In a way, when you think about the formula and the charge, you'll realize that they lock together in a very natural way, because what do we get when we have a neutral compound that's made out of 2 hydrogen atoms and 1 oxygen atom? It's water, H2O. Neutralization reactions are between an acid and a base, and they produce a salt and water. And by salt, I don't mean just like table salt. No, I mean an ionic compound. But salt is a bit more, memorable to say, I guess. A neutralization reaction, has an acid and a base reacting to produce a salt, some ionic compound, and water. I give a skeleton for it over here. The HA part right here, that's your acid. So the H is what's going to become the hydrogen ion in solution. The plus means and. MOH, well, that's your base. M is your metal ion, and OH is a hydroxide ion that can be released in solution. Some bases are not basic in its exact way, but they all end up creating hydroxide ions when they're in solution. In that reaction, an ionic compound is produced. It's made from the non-metal ion of the acid and then the positive metal ion of the base and water. So that's the skeleton really for any neutralization reaction. A simple neutralization reaction using a strong acid and a strong base is hydrochloric acid plus potassium hydroxide produces potassium chloride plus water. I thought I would show that one as well, and then you're going to see a similar reaction in this lab today as well. So here we are. Test tubes. I wish we had a better color to show this. I wish I had a better camera to show this color better. It's really pretty. We'll do the reaction between hydrochloric acid and potassium hydroxide just now. First of all, get a little bit of HCl, hydrochloric acid. Hydrochloric acid is very often used as an acid in high school chemistry courses. It's a strong acid. It dissociates completely into hydrogen and chlorine ions. So it's good for solving simple problems in inorganic chemistry. I'm going to make this a little bit more interesting. I'm going to use what's called a pH indicator. The pH indicator I'm going to use is called phenolphthalein. I've actually shown it to you before. Goggles. You never need very much of a pH indicator. I actually put in too much here. It's not a big deal, but it's not necessary. Can you put this back there?
Where?
There. Potassium hydroxide is, here we see it as
Should I wash my
pellets.
hands out first?
You're fine. Here we are looking at the test tube in the middle. I hope that you can kind of hear that a little bit.
Yeah, so they can hear it.
Yeah, I'm going to try. What you're seeing, that bubbling, is due to the heat release by the potassium. It's due to the heat release that's happening in that reaction. If I put my fingers around this,
It's hot.
it's hot. Okay. It's starting to actually kind of have a bit of a salty smell, if you know what I mean.
It's going to start getting a pinky color.
Should. The salt that we see here at the bottom, given that we're not seeing any further reaction, that must be some potassium chloride that's already formed. I was wondering if some potassium hydroxide was just sinking to the bottom without reacting, but that doesn't appear to be the case.
Make them see. Let them see. Shouldn't you be wearing gloves?
No, it's okay not to with this, as long as I'm being careful with not getting the powder on my hands.
There's
There.
the pinky color.
If you, some of you might have been able to spot there what happened just
There's some more
momentarily.
Right there.
We're starting to see some of the pink color. That's actually not the potassium hydroxide or the acid. That's due to the phenolphthalein, which, although it's being added in very small amounts, switches color depending on the acidity or basicity, depending on how acidic or basic the environment is. The really cool thing with phenolphthalein is as soon as I've added as much acid as I have base, within a very tiny margin of error, as soon as I've added the same amount of each, it switches to very pale pink. If I go into deeper pink, that means I've overshot it. And if I keep adding the base,
There's
nothing
pink
will happen. It'll
right
just
at the
stay
bottom.
pink.
Pink right at the bottom. I can show them.
Hoping to keep going until there's enough of that, until that's all become clear. Okay.
It's really pink at the bottom.
There.
There.
And that's it. It's getting more and more difficult. It's that the pink is sticking around for longer. You actually get to a point where if you add the tiniest fragment
Too much?
of the base,
There
that it turns a deep pink. You don't want to overshoot that point. In fact, let's see what happens if we stir this up a little bit. One thing is the reaction's continuing.
Actually on the bottom.
You can sort of see that pink turning up right there. The good thing with once you've reached the equivalence point, once all of the acid has eaten up, once the base has been eaten up by all the acid and there's no extra of each, it's actually relatively safe. It's not a strong base and it's not a strong acid. It's just potassium chloride, which you don't want to consume, but it's not as dangerous as is an acid, a strong acid or a strong base.
What's the yellow one?
That's iodine.
More dangerous or less dangerous?
So that was the neutralization reaction, and now those substances are out of the way, but we're going to kind of revisit that a little bit later. The final kind of reaction I want to show you is a combustion reaction. Combustion reactions actually can be described quite broadly as a rapid reaction of a substance with oxygen to produce heat. In most high school chemistry problems, the burning compound is a hydrocarbon. So as a skeleton equation, that would be this right here. The CXHY here just means a compound that's got some carbon in it and some hydrogen. And that's it. Reacting with oxygen to produce carbon dioxide and water. That, of course, is a skeleton equation. I'm not telling you how many carbons, and I'm not making any attempt to balance it. Here's an example of a balanced chemical equation that you might find useful for your balancing chemical equations worksheet that I posted recently. burning lighter fluid. Here's a balanced equation for that. Lighter fluid is also called butane. Butane is C4H10. If you shake a lighter, you know that it's a liquid. When you spark the lighter and you let the pressure out, the butane comes out as a gas and reacts with oxygen that's in the air because you sparked it with a flint. In this balanced chemical equation, 2 of the butanes react with 13 oxygens to produce 8 carbon dioxides and 10 water molecules. Hey, also, notice these physical states. The butane, the butane is present as a liquid. That's the little L right there. Oxygen, of course, is a gas. Arrow for creates. Carbon dioxide gas. And this is a bit of an unfamiliar form of water in a way, or not. You don't see this as often. It's water as a product that is in the form of a gas. Why is it in the form of a gas? Well, it'll be obvious to you. When you're burning a lighter, you're making a flame that has a lot of heat, and within that heat, water is not going to just flow as a liquid out of your lighter. It's released into the air as water in the gas form. So those are the different kinds of chemical reactions that I want you to be familiar with. And I've gone through them with balancing chemical equations and so forth. What I'm going to do now is I'm going to show you a variety of chemical reactions, and I'll tell you which one is which in terms of which reaction is which that you're looking at, and then we'll work with that. So, just a moment. Okay, here's the first reaction. In fact, you've already seen it today, at least once. I've already talked to you about it, in fact. But there it is anyways. In fact, we have 2 of the same kind of reaction happening right here. And I hope you are listening so you know which kind it is. Methane is a hydrocarbon. In this case, for CXHY, the X is 1, the Y is 4, CH4. It's reacting with oxygen that happens to be in the air. Hopefully, you can balance that chemical equation because you've seen that before. So that's reaction number 1 for today's lab. Done. Reactions 2 and 3 are a little more complicated, so I'll show them to you now and talk a bit about them as we go. That's cool. That's really weird. Never seen that before. All right, hang tight.
You can show the camera at it. This isn't even charging.
In the case of this reaction, I have the following. I have magnesium metal, which you've seen before. It's this kind of like spool of shiny metal. You know already, I think, that this is a very reactive metal. I'm going to combine this magnesium metal with an acid, with weak hydrochloric acid. By now, Chemistry 11 students, you will know that 0.5 molar means 0.5 moles per liter. And you may or may not be aware that that's a relatively weak solution of hydrochloric acid, but definitely strong enough to use for this type of a lab. There it is. I have an Erlenmeyer flask here. I'm going to take a piece of this magnesium metal and I'm going to put it inside 50 milliliters of the acid. Also, I'm going to get something else to make this more interesting.
Want me to show the charcoal to them?
Yeah, you can show them the charcoal, sure. You could even talk to the internet about that.
So this is the charcoal, and it was getting burned on here, and it just has this strange white color.
Okay.
You see it there?
Thank you, Isa. You can put that there. I can take care of that. In fact, you can throw that away.
Okay.
Soap. Here's the soap. Here's the soap. Good. For this reaction, I'm going to, having added the acid to this flask, I am then going to add magnesium to the flask also. I will seal that up rapidly. I will then make a connection between this flask here and this beaker right here. This might be becoming familiar a little bit here. There will be two reactions, reactions 2 and 3. Reaction 2 will be what happens inside here. Reaction 3 will be what happens at the in the beaker. So let's measure out our acid. $50 milliliters. We need the Bunsen burner running for this. We'll get it started again, I guess. Striker. All right, 0.50 grams of magnesium. Chemistry 11 students, I'd be very impressed if you are able to calculate for me the volume of the density and then the volume of gas that's going to be created in this reaction. Reading forward to the section on stoichiometry, using a balanced chemical equation. Some of you should be able to do that. Here goes. Turn off the lights. Stand right there. Put your hand across. You want your hand on there, on the flask, not on the tube, but on the flask, firmly. Thank you. I think a lot of you will already have seen this, but I'd like you to look at it with fresh eyes. Recognize that you're seeing two reactions here. All right. Okay, go ahead, Isaac. This is actually reaction 2 right here, you're seeing. Okay, and we'll stop that. And could you keep holding that, please? Thank you. Part of the lab is to give the temperature of the solution. Could you please keep holding the flask? Thank you. You've seen the pop test already. Keep holding that. Turn off the Bunsen burner.
About 28.
Yeah, and you can report to us the temperature that you see.
It's almost about 30.
Let's stir it around. My lab assistant is measuring the temperature.
It's a little over 30 now, as you can see.
Bring the computer? Okay. You're going to hold that while I bring the computer over. So, back, you know what? Here, I can hold it. It's fine. You'll see that there's an elevated temperature lining up and there. That the highest temperature I've seen. Did you just see, what was the highest temperature you saw? What was the highest temperature you saw?
In what?
In here. How hot did you get?
I think that's the hottest.
Okay. So we're seeing a peak temperature here of 33 degrees Celsius. And the temperature in the water started out at about 22 degrees Celsius. So all of you who've looked at the exothermic versus endothermic lesson that I posted earlier today are probably going to be in a place to say whether this was exo or endothermic. So that was reactions 2 and 3. Reaction 2 is what happened in the flask between the magnesium and the hydrochloric acid. Reaction 3, couldn't measure temperature for that, but we saw the rapid explosion really that was involved was what happened to the gas that came out of the tube. So those are 2 reactions right there. So let's put this away. Reaction number 4. Reaction 4 will be copper plus silver nitrate. I'm just going to take this to the disposal area. This reaction is less dramatic, but it's still very interesting. What we have in the case of this reaction is silver nitrate. Silver nitrate at a 0.2 mole per liter concentration. Chem 11, that means more to you. For this reaction, I also thought I'd bring out some of what I created for the moles of copper and iron lab. I kept this stuff. Thought it might come in useful someday, and it is. These are those crystals of copper I talked about. Now I'm going to try something and it might not work. I want to see if we can get a really nice close-up look at those crystals. So I'm going to put this to the side here, and I'm going to put some of these crystals in this container right here. That's good enough. This may or may not work. So I'm going to angle the computer like this here, and the light will be like this. There. It's as good a shot as I can get. So let's have a look at, there's a lot of glare right there. All right. That's not showing up super well. No, that doesn't help. So what you should be able to see, I was really hoping we'd be able to see those copper crystals. You should be able to see at least, no, you can switch it off. Switch it back on. Thanks. You might just be able to see the kind of, the fancy word for this is dendritic, the branching shape of these crystals right here. I'm just trying to find a way to have them show up. I'm going to try something. I got this from home for a reason. I'm going to line this up right there. Yeah, it's kind of showing up a little bit. You can kind of see those crystals of copper. Could you try shining the light on it from a number of directions, Isa? Okay, and
that works.
Okay. There, that's about as good as we're going to get. Switch the light off, please. Thanks. Actually, that's a lot better. The LED light was a bad idea. Notice that the crystals have this kind of a branching structure. And obviously notice they're brown because after all, this is copper. Now I'm going to add...
showing in the beaker.
Yeah, the point is I was showing it up close. I'm now going to add some of this silver nitrate.
Okay to hold?
Yes, that's just copper. That's okay to... don't put your hand in it, though, please.
I can maybe show them crystals.
This is interesting. This reaction is interesting because it's basically instant. It's not super dramatic, but it's an instant reaction. Oh, but we want to do the temperature, don't we? Let's get a thermometer. My assistant is getting the thermometer. Okay, I'm getting a facial expression there.
Put it in?
Wait just a sec. All right.
1,
So,
2,
actually, you know what we're going to do?
what?
I'm going to get a baseline temperature. Could you put that away, please? Yeah. Okay.
I need to get a better look.
Okay. I think what I will do actually is I'm going to put some of the silver nitrate directly into this test tube. That way I'll be able to measure the temperature of it before the reaction. Yeah, that's definitely enough of it. And put this away now. Don't touch, please. Don't touch any of this stuff, thanks. When you're working with such a small amount of any substance, any kind of temperature change is going to be pretty subtle, especially with a reaction like this. Nonetheless, it's an interesting question. Are we going to see an increase in temperature, and if so, how much? Because again, you saw the lesson earlier today on energy and chemical reactions, so you'll be familiar with exo and endothermic reactions.
Can I put it in?
Actually, what you can do is go like that, put that in there.
I thought I was doing it.
Okay, don't touch that, please. Let's get the temperature. Temperature of the silver nitrate solution before being added is 21.2 degrees. We won't even use that thermometer. I'm just going to add the copper direct here.
Hey.
There.
It didn't do anything.
Oh, it certainly did.
What did it do? froze?
And the temperature, the peak temperature is not doing much.
Is it hot?
The reaction has already happened. I'm seeing a temperature now of 21.5. I think it's as high as I've seen it go. Maybe, yeah. So it's gone up by maybe 0.3 degrees. Some of you, critically minded, will say, Mr. Coop's making it up. And maybe you're right. Because realistically, that is a very small temperature change. But at the same time, do I think there's a temperature change? Possibly. Do I think it's likely that it was a decrease? Well, there's certainly no evidence of that. The best evidence here would be that we have either no temperature change or a very small temperature increase of maybe a fraction of a degree.
It's warm.
Oh, look at that. Okay. I take that back. The temperature is now 22 degrees Celsius in the solution. Let's move this around a little bit, see if we get
so now
any.
It's like frozen? And what are those crystals?
Yeah. I'm going to take this out. I'm going to put this in here. Don't touch that, please. In fact, I'm going to put this all away.
Should we put more copper in?
I'll take, no, we don't need any of that. Or maybe we will, actually.
Did it turn into crystals here?
Yes.
Should I show them?
So again, peak temperature, it looked like we were reaching there, was turned out around 22 degrees Celsius, starting out at about 21.2. So I'm actually at this point going to say that there was a very small increase in the temperature. My lab assistant would like me to add the rest of the copper.
Yeah, can I bring it?
That seems like not a bad idea.
Can I show it to them?
You want to pour it in? Yeah. Okay, I'll hold the test tube, hands off. All you do is you touch the beaker. Okay? Good. All right. So what you should now be able to see is, well, it's a bit of a mess, isn't it? At the same time, what I'm hoping you can really see here is that distinct color of copper is gone, has disappeared. It's not a coppery color anymore. It's like that because the copper has entered solution and we have a silver color that has appeared on what were the copper crystals. So there shouldn't be any mystery. Don't touch those, please. Put them away and go wash your hands. There shouldn't be any mystery now about what kind of reaction that we had right here. So again, I'm going to try and see if we can get a bit more of a close-up right here. So let's get the magnifying glass. Is it going to work? Is it going to work? You can kind of see that branching a little bit there. The crystals of silver, just like the crystals of copper, almost look fluffy. There, that's actually a pretty good image. They have a kind of a fluffy look to them because the crystals themselves are extremely small. They're microscopic crystals. They form very quickly. Crystals that form very quickly, not surprisingly, are really small. But while once we had tiny crystals of copper, now we have tiny crystals of silver. This also doesn't show up perfectly well, but maybe we'll come back to this. You might just be able to see, at least what I can see when I look at this, a very slight hint of blue. What I'm going to do is I'm going to let this sit. I'm going to stir a little bit. I'm going to let it sit. And we'll come back later to see if there's any more obvious of a change from the clear solution to a blue by the end of today's lab. just going to do a bit of cleanup. Did you wash your hands, Isaac?
Yeah.
Good. The next reaction I will show you is reaction 5. Oh, okay. You like this.
You might be able to.
Reaction 5 involves something many people have come to know and love. It involves a substance called hydrogen peroxide. I had a student who was lucky enough to be in here last week. We're working with this substance. Hydrogen peroxide is a very unstable compound. Notice that there's a little hole in the top of the cap. This is because if you let this sit long enough, gas will collect inside here and the bottle might explode in storage. You wouldn't want a high concentration hydrogen peroxide spilling all over your chemical cabinet. So they put a hole in the top. For this reaction, I'm going to use, I think I'll use just 25 milliliters of hydrogen peroxide. Goggles, Isaac. Goggles.
So, when is this video gonna be done, Dad?
It's going to be a little while.
Huh?
It's going to be a little while.
Like an hour?
Not as long as that. For this reaction, I'm going to produce first a small amount of a sodium iodide solution. It calls for potassium iodide, but I don't see why sodium iodide shouldn't work just as well.
Yeah. It's just reaching an hour we've been doing this for.
Yeah. You have a point.
It's 59 minutes and 22 seconds.
Yep. I'm working as fast as I can. To do all of these reactions. It's difficult. So we're going to work with, you can just watch, don't touch anything, please. So I gotta apologize, a lot of people find this reaction a little boring. Sorry. So this is making a solution with the sodium iodide. You might want to do a bit of research on the website ThoughtCo. That website will tell you something about this reaction. It'll tell you that in fact, the sodium iodide, although it's used to make the reaction start, is not actually a reactant. And of course, therefore, it's not part of the products, but it's used to make the reaction start. If I were to have sealed this bottle, dumped in a bunch of sodium iodide, and then sealed it up again really quickly, well, it would be a very interesting result, as you're about to see. This is a 1 milliliter graduated cylinder. There we go. This always goes a bit better if you have food coloring. But the good thing is that the iodine, the sodium iodide, has a habit of very slightly dissociating and forming elemental iodine as part of this reaction. Elemental iodine, as you will recall from earlier, is amber brown. Let's see what happens. Oh, would you look at that?
Whoa,
It looks like there was a reaction.
Was it elephant's toothpaste?
Yes, this is the ever favorite elephant's toothpaste reaction.
Can you do it again?
Forgot to do the temperature.
It goes down really fast.
Yeah, it does. I forgot to do the temperature.
So you'll have to
I guess I have to do it again.
Yay.
Oh boy, it's warm. Actually, you know what?
No, please do it again.
I think we're gonna be fine. I'll tell you this much. Hey, you can put your hand above the beaker. Put your hand right here. Okay? And remember, you're going to wash your hands after this lab's done. You can also touch the side of the glass. Okay? Feel that, eh? How would you describe how that feels when you put your hand on it, lab assistant?
Warm but not hot.
Okay, and
So isn't it supposed to be hot?
temperature that I'm getting in the middle of this reaction, 51 degrees Celsius. Clearly, it's released a lot of heat, given that this was, of course, just a moment ago, air at around 21.5 degrees Celsius. No, I won't do this again. Maybe when you're in my chemistry class in the future, lab assistant, you can see it again. Yeah.
That's a long time, Dad.
Okay, fine.
Next time, pick a different color. Is there a different color that you can color? Is it the red?
All right, so let's figure out what the next reaction is. That was reaction 5, peak temperature 51 degrees Celsius. Reaction 6. Reaction 6 is going to be copper sulfate plus barium chloride. The solutions are already, well, they're already created. They're aqueous solutions. Here we are. I haven't done this reaction yet, but I'm pretty much sure it's going to work. This very pretty blue solution is copper sulfate in solution. What you should be able to see is that it's very nice and clear. I heated this up yesterday and made sure it was all dissolved. Here we have another clear solution. You can see my hand through it, albeit that the glass is a little bit... There we are, that's better. 0.10 molar barium chloride. Barium is a big atom. If you look at where it is on the periodic table, it's pretty far down. I'm not going to aim for any particular amount that I use. Reaction will be simple. There. Cloudy. Clearly you can't see my hand anymore because clearly it's no longer clear. Thermometer. Measure temperature. Assuming that was at room temperature, which obviously it would have been at room temperature. Let's try adding a bit more. Okay. We have 20.5 degrees Celsius. 20.5. That's actually a little bit lower than I might have expected. You know what I'm going to do? I'm going to come back to this later on, if I remember to, and we'll look to see if the temperature has come back up a little bit. I find this interesting that this is actually a bit lower, just slightly lower than the 21.2 that we've been seeing. Not a huge difference, but it certainly is not 21 point anything. We're seeing, a 20.5 degrees temperature, and it's instead of clear blue, it's now a milky blue color. All right, we'll put these away. Okay, out of the way. Here I have two solutions. Let's be proactive about this and get the temperatures now. One solution is a strong acid, the strong acid, hydrochloric acid, and the other is the strong base, sodium hydroxide. I had to label them yesterday because they're both clear liquids. Otherwise, then, how would I know which was which? In actual practice, it doesn't matter, but it's nice to know. So let's let that sit for a moment and get those temperatures. And what I've got here, could you do that at the back, please, Isa? Yeah. Is a thermos. So, there we are. As you all know, a thermos allows you to isolate the temperature of a system because it releases thermal energy to the system or exchanges thermal energy with the system relatively slowly. Also, I have some phenolphthalein pH indicator. Our temperature of the acid, 21.1. Temperature of the base, 21.1. Okay, that's interesting. And I'm only going to keep one of these two thermometers in here for this reaction. And I'm going to cover that off. Let's put the pH indicator, the phenolphthalein, into the acid. Before I add this, I would like you to think back to what I did a few minutes ago and tell me, will it turn pink or not? Just think about this. Before you see me do it, is it going to turn pink? Well, anyways, you're going to find out now. No, it didn't. Okay. I hope you already knew that. I'm going to add the sodium hydroxide first to the thermos. And now I'm going to add the hydrochloric acid. And then I'm going to seal this up, cover it up as best I can at least. I wonder, do I have anything better? I don't. There, this will insulate a little bit better. I'm going to use this foam to cover up the top immediately after I add the HCl. And the temperature is now 26.5. And where are we at now? It's now reached 27 degrees. I wished I could have shown you, but it's gone away now. I'll tell you what I did see. The moment I poured the HCl into the solution, it turned hot pink. Then, interestingly enough, it went clear again. And you can give thought as to why do you think that was, that the moment that hydrochloric acid was exposed to the sodium hydroxide, we saw that pink color, but then it disappeared because...
Can we do it again?
Is there any color in there, lab assistant? No. It looks like clear water. In fact, if you were to drink some of this, I won't, but if a person was to drink some of this, if the reaction had been done perfectly with perfectly balanced chemical amounts, what would it taste like? Well, it would taste salty.
Will it die?
Specifically salty because it contains sodium chloride.
You can do
Hopefully, as well, by now, and you can tell me the other product of this reaction. Peak temperature turned out to be 27 degrees Celsius. There are YouTube labs for anyone who would like to take a more advanced examination of this that will allow you to actually make statements about the amount of chemical energy that is released as thermal energy in this reaction based on the kilojoules per mole of the, in other words, it will tell you what the enthalpy change is of this reaction based on kilojoules per mole. You can try it if you want. I use 100 milliliters of 1 molar HCl and 100 milliliters of 1 molar sodium hydroxide in that reaction.
You can do it again.
Yeah. If you're interested, there's a activities on that topic, although it's beyond the level of Chemistry 11 anyways. So that was reaction 7. So let's think back. I think we've done all our reactions. Oh yeah, we were going to get the temperature again of the barium sulfate. And the temperature is at 20.5. My conclusion, personally, is that there is no detectable temperature change for this reaction. If I had let this sit and the temperature had come back up, I would conclude that the temperature had indeed gone down a little bit and then returned to normal. I think it's been sitting long enough that I could say with some confidence that this thermometer measures a little bit low. We can examine that possibility. Actually, no, we can't. You know what? I won't even bother. Okay. So now we're sitting about 21 degrees Celsius. Again, would we, within a margin of error, say that there's a detectable temperature change? I think that that's open to argument. At most here, we're talking about movements of no more than 0.5 degrees Celsius. The other temperature changes that we've seen in today's lab, I think, are a lot more definitive. The last thing I want us to look at is the final state of that solution here. And it's a bit of a mess. Hopefully you'll be able to see that it's got a slight hint of blue. What you might also be able to see is that the color of the copper is back. Why is it back? To give a simple answer to that, it's because I added way more copper than I needed to react with all the silver that was in the silver nitrate. Having done that, all of the silver ions have been eaten up, and some copper is still left over. So, but be that as it may, we do have some of the blue solution, the blue color that we expect of a solution that does have some copper ions in it. Going forward, Chemistry 11, you'll be able to make statements for me based on my volumes added, maybe around, let's say, 10 milliliters of silver nitrate. You'll be able to make statements from me about how much silver was produced in this reaction. But you don't have to worry about that right now, because that's Unit 7. That is everything I wanted to cover today. So you've seen many of the different kinds of chemical reactions in my lesson. You're familiar with them from the skeleton equations. And I've given you a lab here where I've done many of them, and I'm hoping that you at this point as well will be able to identify the reactions that you saw and to balance those chemical equations. If you'd like any help with balancing chemical equations other than, of course, myself, there are various online resources. If you want to, I don't know if you want to call it cheating or just want a bit of a helping hand, you can look for online chemical equation balancers. It's all there for you. Going forward, know how to balance a chemical equation, know what a balanced chemical equation is, and use the resources at your disposal to balance those chemical equations and to identify the chemical reactions that you saw. I hope that helps, and that is all for now.